Hello everyone. My name is Dr. Haknavas. I am affiliated with the Marine Engineering Department at Military Technological College, Muscat, Oman. The title of my research paper is Wideband Antenna with Low Port-to-Port Coupling for Monostatic Antenna-based full duplex nodes. So I will proceed for this presentation like this way. First, I will discuss about the in-band full duplex and the motivation of this monostatic antenna for such application. Then I will discuss the hypothesis for this work and some examples of the relevant previous works uh, based on such shared aperture or the monostatic radiator for in-band full duplex or simultaneous transmit and receive application. And then I will discuss the structure of the presented antenna, which is the wideband monostatic antenna, and that antenna implies the differential feeding or the balance feeding to suppress the leakage from the transmit port to its receive port through the this differential feeding. And I will discuss the characteristic of the differential feeding and how the characteristics they contribute towards the achievable levels of the isolation or the reduction in the interport coupling. Based on this differential feeding, I will discuss the performance characteristics of the presented antenna, including its impedance matching characteristics, port-to-port coupling or interport isolation, and of course the gain performance. And finally, I will conclude this presentation. Uh, so the motivation of this work is to realize antenna for in-band full duplex or single channel full duplex application. Such applications, these in-band full duplex or simultaneous transmit and receive application or single channel full duplex that has the potential to double the spectral efficiency or the throughput of the system, but the performance of the in-band full duplex operation that is highly dependent on the suppression of the self interference, that is basically the leakage from the transmit port to its own receive port, because the antenna or that the system is working on the same frequency for the transmit and the receive links or uplink and down links. So in that case, there is a coupling of the transmit signal to its own receive chain. So we have so many techniques for the self-interference cancellation to achieve good decoupling or isolation between the transmit and receive channels. And all of those self-interference cancellation, either analog or digital, they basically focus to suppress the leakage so that the signal of interest, which is the actual signal coming from the remote transmitter, that is basically recovered in healthy way. And the effectiveness of such self-interference cancellation or isolation techniques, they define the intended isolation between the receiver and its co-located transmitter. Most of the time, shortly I will show the calculation. The self-interference cancellation amounts or the levels, they are defined by the transmit power and the bandwidth of the system. But there is no single technique which can realize very high amount of or levels of self-interference cancellation. So there are the self-interference cancellation techniques which are employed both in analog and digital domain. And one of the critical thing is that most of the isolation that must be suppressed at antenna level, because if that isolation is not suppressed, I mean that cancellation is that leakage is not suppressed or self interference is not suppressed, then the actual signal of interest that will be overpowered by this leakage, which is very high in power. So, and this will also saturate the analog to digital converter in the receive chain. So the antenna design with the capability of high isolation over the wide bandwidth, that is very challenging. There are several antennas, there are various antennas which provide good isolation amounts, but those amounts, they are basically very high level of the isolation, but that the bandwidth, that is the narrow. So the focus of this work, that is basically to achieve high isolation over wide bandwidth. So this is one illustration of the in-band full duplex where we have a two configuration. The first configuration, that is basically uh, in-band full duplex with the shared antenna, and we can use the circulator, but circulator doesn't provide uh, too much isolation, which is in excess of like 100 dB. And the second configuration, that is called bistatic. So in first configuration, on the top we have the same transmit and receive frequency, but we have a single antenna for transmit and receive purpose. But in second configuration, we have the separate or dedicated antenna for the transmit and receive purpose. Especially in shared antenna, the configuration given on the top of, I mean the first configuration, in-band full duplex with the shared antenna, that is very realization of such communication is very challenging because we don't have any way to separate between the transmit and receive signals where the transmitter and the receiver of the same node, they are placed very close by each other. And because we have only one antenna, so we cannot basically separate transmit and receive antenna. So this is the challenge for in-band full duplex based on the shared antenna or monostatic antenna, where we have a single aperture or radiator for the transmit and receive application. So one of the question, that is like how much isolation we need. So if we successfully suppress the leakage from the transmitter to its own receiver, then we can recover the signal of interest without any distortion. So the self-interference cancellation or the amount of isolation, that is defined by the transmit power. And this transmit power is the power radiating from the transmitter. So in this case, you can see that if we suppress the transmit power up to the noise floor, then we can recover our signal of interest without any damage. So that is the important, that the transmit power, that will define the amount of isolation. So here you can see, as I mentioned earlier, that the self interference cancellation, they can be deployed both in analog domain, which is RF radio frequency domain on the antenna stage, and also after the antenna. So you can basically deploy this where you sample the transmit power and you subtract that one from the coupled signal. So, but this is again narrow band because these are all phase inversion techniques. And then we have a digital domain processing to achieve isolation between the transmit and receive chains. So the hypothesis for this work is that a dual port monostatic antenna, where we have an antenna, single antenna with two ports, and those two ports, one of them will be used as a transmit port, other as a receive port. So a dual port monostatic antenna can be designed with two major characteristics. One is comparatively wider impedance bandwidth, where the antenna is well matched. It accepts the power in that range of frequencies, and it also the other port, that is the receive port, with the same bandwidth. And the second thing is, most of the transmit signal, that is suppressed on the receive ports of the same antenna. So this is basically the low coupling between the transmit and receive ports. Here are some examples. You can see in all these three works, the isolation levels are good, but the bandwidth is narrow. So if I consider the isolation and the bandwidth product, that will be very low. So in this work, the challenge is to design antenna with wide impedance bandwidth and high isolation. So the structure of the antenna is presented in this slide. Here we have a 3-port antenna, and we have a stacked structure. I mean 3 substrate layers on the left side. So we have one port as a transmit port and 2 ports as a receive port. And then the transmit signal to both receive ports that will be equally coupled. If I use a differential circuit on port 2 and port 3 of this antenna, then I can suppress this transmit signal on the receive ports, and this can give us effective isolation between the transmit and receive ports. And both port 1 and the differentially excited port 2 and port 3, they are dual polarized. So we will get the isolation in two ways. One is like polarization, the polarization diversity, which is basically orthogonal polarization. For example, the transmit is vertical and the receive is horizontal. And the second thing is the differential feeding. So that will give us the good isolation between the transmit and the receive port. So for this structure, the receive operation is the balanced through balanced operation or through differential excitation, and the transmit port, that is the single-ended. And this is a unidirectional antenna. I mean, it will radiate only in one direction, which is the advantage of this antenna, because we don't have a radiation on the back side. And such antennas, they are preferred because we have a very high front to back ratio. So for differential, and you can see in the lower figure, you can see the radiation pattern both for the transmit and receive ports. However, for the differential feeding based isolation, the important thing is the performance of the differential circuit. Because as I mentioned earlier, from port 1 to port 2 and from port 1 to port 3, we have the same amount of coupling. But this coupling suppression, I means taking the difference between these two coupled signal, that totally depends upon the performance of the differential circuit or the balance circuit. So on the top right, we have a differential circuit which can provide us good uh, characteristics. Two main characteristics of this differential circuits are the magnitude balance and the phase balance. So this will be used as a differential circuit. So you can see on the top right, we have a port 1 and then we have a port 2 and port 3. So we can connect port 2 and port 3 of this differential circuit to our antenna, and then the port 1 of this differential circuit, that will be used as a receive port. So this is the depiction of the performance characteristics of the differential circuit. You can see as the phase balance and the magnitude balance, they becomes good. So you can see in the center where the phase imbalance, that is 0, and the magnitude error or the imbalance, that is 0.1 dB. So we can get very high isolation, that is like 45 dB. And if the phase balance, imbalance, or the magnitude balance, they deteriorate or they are reduced, then we will get less isolation or the suppression in that case. So here is the basically the performance characteristics of our balanced circuit or differential circuit. So it provides good impedance matching, which is S11, S22, S33 port matching, and S21, S31. That is basically uh, the performance characteristics. They should be balanced. I mean, their magnitude should be same and their phase should be 180-degree out of phase. So you can see this and this balanced circuit or the differential circuit that provides. So 3 dB insertion loss is already there because power splits half. So 3 dB, anything on the top of the 3 dB, that is like the insertion loss for this. I means the loss inside this circuit. Now if I use that circuit, differential circuit, with our antenna, I means the two ports of the differential circuits, they are connected to receive ports of our antenna, then you can see here that the antenna, that will give us the isolation. In fact, this graph is basically the interport coupling, and inverse of the interport coupling, that will be the isolation. So you can see that our antenna is well matched over wide impedance bandwidth. We take the minus 10 dB return 10 minus 10 dB reflection coefficient as the reference, and then S21, that is basically coupling between the transmit and receive ports. So you can see here that impedance bandwidth is in excess of 1 giga from 2 to 3 giga, and the isolation, that is Our interport coupling. Interport coupling is less than minus 60 dB. Our isolation is better than 60 dB. As I mentioned earlier, that the isolation and interport coupling, they are reciprocal of each other. So in this work, I have presented a monostatic antenna system. Why I say the system? Because antenna with the differential circuit, and this provides very reduced level of the coupling between the transmit and receive port, or I can say this antenna provides good isolation between the transmit and receive ports. So this high interport isolation is achieved through the polarization diversity and the balance feeding or the differential feeding in this case. And the characteristics or the parameters of the differential circuits are they present good isolation because their balance is good, magnitude balance is good, their the phase balance is good, so they can suppress the coupling over wide bandwidth. That is basically the main contribution of this paper: wide impedance bandwidth and wide isolation bandwidth. So this antenna achieves very high impedance bandwidth and very high isolation over wide bandwidth. So this is basically the performance characteristics of this antenna. The implied feeding network that provides effective self-interference cancellation across wide bandwidth. So this is basically the property of this presented antenna, or the performance contributions of this antenna. Then how the wide impedance bandwidth is achieved, that is intrinsically or inherently from the stack structure of the antenna. So we achieve the impedance bandwidth over 1 giga, that is starting from 2 giga to 3 giga. So this presented antenna that provides us more than 60 dB isolation across this wide bandwidth, which is basically 1 giga ranging from 2 giga to 3 giga. So this works is a good contribution to in-band full duplex monostatic antenna, because the monostatic antenna is considered as the good candidate for the in-band full duplex to achieve good spectral efficiency or the throughput from the system. Ideally, the in-band full duplex provides the doubling the spectral efficiency or the throughput of the system, but practically that is limited by the isolation between the transmit and the receive chain. An antenna stage is the most critical part in band full duplex or simultaneous transmit and receive chains to provide good isolation between the transmit and receive chain. And the most of the previously presented antennas, they have narrow impedance bandwidth, narrow isolation bandwidth. But this antenna provides wider impedance bandwidth and wider isolation bandwidths, and these are the contribution of this antenna. If you have any question related to the in-band full duplex antenna specially presented in this work, feel free to contact me on this email. I will be more than happy to answer your questions regarding such antennas. Thank you so much. Take care of you.